Hello viewers, welcome back to the audio series segment from Multimagic channel. Myself is Funny. In this particular audio series, we have discussed various topics related to the audio, and all those details are captured in these 5 videos. So you can go through all the details. If you have any questions and queries, you can definitely reach out to us. And this particular video is the sixth video in this audio series segment. And today's topic or project it is on PCM data mixing. This is a very simple project or like kind of a simple algorithm where we'll be discussing about how to mix two different PCM datas. Okay. So on that note, let's jump into the today's content. So we'll start with the agenda. So the agenda, we'll start with what are the prerequisites, an introduction about what is PCM and what is audio mixing, like different details we'll go through. And I will tell about the project block diagram or the basic process flow we needed, and I will also share the GitHub links, and at the end will also discuss about the upcoming projects. Yeah, so on that note, let's start today's video. So prerequisites, so it's simple. So we are all the audio series segment we are doing on the Windows platform, and on a Windows machine install the Microsoft Visual Studio 2010. If not later than 2010, 2022 also works good. I'm using MS Visit 2022 on my machine. So, as I said, this project is not built from the scratch. As I said earlier, we are using it from our mentors' building blocks, which they are used for a pre-startup company called Axie. So now let's jump into the actual content. So in the real world, what is audio mixing means? See, audio mixing is the process of combining and adjusting individual tracks or elements to create a final stereo mix. So these kind of setup you might see in various auditoriums. Like if you go to any party, the DJ that generally use this audio mixers, all those things. He mixes different tunes and things, increases the amplitudes, all those things he does. So, and also in any auditorium or any big functions, a separate guy will be there who take care of all these things such that it is audible to all the viewers. So in general, this is about a very vague thing about audio mixing. Of course, there are a lot depth you can add to it, but for this particular project, it is just good enough to know what, in general, what is the audio mixing. And also, there are two approaches: hardware audio mixing is there, and software audio mixing is there. Of course, whatever picture you are using is a hardware mixing where you need a different physical devices called mixers, mixing consoles, blend, process audio signals, and a lot of hardware and configuration and softwares are needed for this particular hardware audio mixing. But software audio mixing, in general, it is purely an algorithm to combine the samples from the incoming data with the required configurations. So we in this particular video we will be discussing more about the software audio mixing. In fact, we'll be discussing the algorithm for the audio mixing. So let's move on to the next slide. So before going more into the project or more about the mixing the PCM data, we'll just quickly recap what is a PCM data. See, in general, PCM means it's a pulse code modulated data, pulse code modulation. See, we have discussed it in the earlier videos. An audio wave is nothing but a collection of samples at particular intervals of time. It's called where each collection is called a sample, and that sample we are representing in a digital format. And if there is any specifications for that representation, that particular representation is called pulse code modulation. So typically we can say the raw data and the PCM data are often interchangeable. It means like, yeah, so far we are in this audio series we are capturing the raw audio data, and the data is written into the file. So that file is called raw audio data, and it is also called as a PCM data if you are capturing that raw audio data with a certain specifications. Like so far we are doing, right, we are giving the sample rate, samples frame for frame, bit rate, channels. So all those with these specific details only we are capturing the audio data and then storing it in a file. So the raw data is also called as a PCM file, provided you have given enough specifications. That's what we have doing so far with the port audio things in the previous projects. So if there are no specifications, then that is called raw data. If specifications are there like that, then it is called a PCM data. Okay, so just want to give this information such that users don't confuse between the PCM data and raw data. Okay, so let's move on to the next slide. So what at high level, what is mixing? What is mixing? PCM data means. See, let's say you have samples from one file or from one audio file and have samples coming from the other audio file. So if you mix these two samples at, so let's if you take sample one here and let's say take sample one here, mix this, you get a result like this. And if you take a sample from here and if you take a sample from here, you add this, you will get more sample value. So like that you can mix the amplitudes of the samples and then you will get the final audio or final PCM data or final data like this. So this is at high level called as mixing of PCM data. But there are a lot of, we need to think about a lot of things in the process of mixing. So first we'll discuss that in this slide now. See, at high level mixing is good, but in the digital audio world, the sample is restricted by a range of a chosen representation called bit depth. See, each sample, so each sample here, it is represented in the form of binary, and how many bits we need to represent that data in digital world, that is what we typically follow the norms. For example, let's say if you take this 16-bit signed integer, so that values range from -3 to 760 to 3 to 768, which is 2 power 15. So now let's say in the process of mixing, we take two samples, one sample from PCM file 1 and the other sample from PCM file 2, and we mix it, we got this, we can say, okay, this is good, no issues. But now if you take two samples, each value is 25,000, result value is 50,000. So this 50,000 value cannot be represented in the 16-bit range. So the max value is 32768, but we reached that max out of range. So the data corruption might happen. So we need to maintain bit representation in digital audio mixing to avoid data corruption. Okay, so this is very important thing. So mixing, you mix it like this, but after mixing, data corruption happens because you are sticking to a certain digital format, bit representation format. We need to, at any given point of the time, we need to maintain that representation. So that is the basic thing in any digital conversions or digital world. So now in this algorithm, or we to prevent or to preserve the bit representation in the audio mixing, we choose as one such simple way. So first is we do four simple things. First we rescale. It means like we normalize the values such that the range will be from now -1 to 1. And of course we add those two samples and the resulting value is 1.526 now. So now we need to in actually let's see if there are two higher tones, and if you mix those two higher tones like beep two beep sounds, the resulting will be much more beep sound, right? So we need to avoid such high pitches in the mixing. So in order to do that, I reduce the volume by 10%. In other way, I am just using the 90% of the amplitude values and remaining 10% I'm cutting it off. Okay, that's what meant by reducing the volume by 10%. Okay, so now the resulting value is 1.3734, but the resulting value should be in the range -1 to 1, because that's what how we our scale is from -1 to 1. Okay, so this, let's say now this value should be round off to 1, and this round off is called also called as a in digital audio world, it is called as clipping. It means after a certain threshold you are not taking and considering that particular value, you are just sticking to that particular threshold value, you clip that tip. Okay, so that is why it is called as a clipping in the digital audio world, this round off. So if the value is greater than 1, we round it off to 1. If the value is less than -1, we round it off to -1. Okay, so this is called clipping. And last thing is we again rescale or denormalize the value. So this one is converted again back to the original value. So this bit representation is preserved here. Okay, so if the mixed sample value doesn't goes out of the range, we don't do nothing. If the mixed sample value falls out of the range, then we do all those things. Okay. So for that reason only we rescale it. We do kind of do all these things. Okay. So now this is what actually happens. This is what actually we do in the digital audio mixing without losing any data. We just clip some data. That's all. So this is the actual frame since the amplitudes are from 0 to 1. So let's say it take 16 bit, and here also the amplitude value is 0 to 1. So each values are represented as 16 bit. And then yeah, instead of a pure sine wave now, we will be getting like this, like go here and then do like the peak is bit peak clipped here. So you'll be coming here and then you go here and then you come like this and then you do here and then you come like this. Yeah. So this is how the sine wave looks. The peak is clipped here. So, but there will be not much loss of data here. Just very few amplitude values we are decreasing, which is going out of peaks. That's why while mixing, we need to ensure in the real world, we will not mix the same PCM data, same kind of audio data, like from one particular file or one particular stream, audio stream, will have low frequencies. One particular audio stream will have high frequencies, and then we mix both of them, and such that there will be like no more loss of data. If you take both high frequency, there will be clipping. Okay, so ensure that in the mixing, you ensure you pick the right audio streams to pick. Okay. So this is what about the audio mixing, digital, what is how to mix PCM data, how to visualize it in the form of samples, and why we'll take care of bit representation. In order that what happens, some clipping happens. So these are all the fundamental things needed for the digital audio mixing. Okay. So now finally, this is how the actual process goes. So here I am taking two PCM data, two PCM files, which are captured already, uh, 16-bit with the two channels. So I have two physical files, PCM1 file, PCM2 file on my machine, and the specifications of this PCM is it is a 16-bit data and it has two channels. Okay. So for simplicity, I have after once first we read this file, and then we store all the data information here into the local buffer called buffer1, and each and later we these are the frames here. So for each frame we'll be having certain number of samples. For simplicity, I mentioned here each frame has two samples, and this frame 2 has two samples, and frame n has two samples. So in other words, I can say this particular PCM data we are storing it into a buffer, and then we categorize that whole buffer into frames: frame 1, frame 2, frame 3, frame so on, frame n. Similarly for the PCM file. Okay, so now what happens is when the algorithm starts, it picks the frame 1 from PCM file and picks the frame 2 from the PCM file. So like this 1 2 1 2. So this is from frame 1 of PCM 1, this is frame 1 from PCM 2. So now again, from for each frame, we take each sample and we pass it to this particular algorithm block, and this particular frame from PCM2 file, we pick sample from that particular frame and we pass it to the algo. So to keep it simple, to the algorithm at the end we get two sample values: sample 1 from PCM1 and sample 1 from PCM2, and it keeps on all the samples keep coming in that frame, and once the frame is completed, it again goes back and fetch the other frame from PCM1 and PCM2. Both those frames are passed here, and all the samples inside that frame are passed to this digital audio algorithm, digital mixing algorithm. So now, once the sample is passed to this particular digital mixing algorithm, as we discussed in the previous slide, we do normalization first, and then we add it, and then we reduce the volume, and then we do a soft clipping. And finally, we write that sample value here. So the first sample is written here, and the second sample value is written after computing all these things. So similarly, For all the all the samples inside that all the frames, we are mixing that sample value and then we are writing it to it, but one more buffer called output buffer. So here MF stands for mixed frame. Mixed frame 1, mixed frame 2. These are the samples inside that mixed frame. So finally, after all the output buffer is populated, we are writing that output buffer into a file called PCM file again. So which is of a mixed PCM. Sorry. So to keep it very simple, so we have two PCMs data and then we have, and the output is a mixed PCM, which is a combination of mixing of these two PCMs. And to ensure the data is not corrupt, we do follow certain algorithm. There are a lot of algorithms available. This is one such simple algorithm, provided we are uh, for now, for the simplicity case, we are just passing the PCMs which are both are of same duration. Okay, so let's move on now. So this is the code flow actually. So here we do actually, first we need to read the data from file 1 and store it into a local buffer. So this file 1 bytes is the data from file 1 and we store it to local buffer 1, and this to file 2 bytes is the data from file 2. The file 1, file 2 here is means PCM files and we store it to the local buffer 2. So now what we do, we define how many samples are there, how many frames are there, and for the output. So the number of samples for the output are the what mixed output file is. See, we need, since both the files are of same type, we can pick file 1 or file 2 bytes. But to make it more generic, we have written like this. We pick the maximum. So the maximum here is whatever is the max that bytes we take, and the number of samples is computed from this number of bytes or size of sample, and number of frames is number of samples by samples per frame. So like this we got the number of frames. So we iterate through each frame. So, and for each frame we call this mixer. So in other words, from this local buffer we just pass one frame of information to that particular mixer. Okay, so here we are telling local buffer plus I iteration. So for each frame, current lag is 0 means okay, it will give you the first frame from the local buffer of PCM1 and local buffer 2, which is related to PCM2. So this particular first chunk of data or first frame is sent to the mixer. So inside this frame, we have number of more samples. So now we'll go to this next frame. So what happens after receiving the frame? So after receiving the frame, we iterate through each frame, and then for each frame, uh, from sample 1 and from PCM1 and PCM2, we pass these samples. So indirectly we are taking two corresponding PCM samples from two different streams and we are returning the mixed samples, and then we repeat this process for each samples in the frame. So this is what the algorithm does. So we just normalize it, and then we reduce the volume, and then we do a soft clipping, and then finally we denormalize, and then again we finally return the output sample. So this is one sample value, and this complete process iterates for each sample in that particular frame. Once the frame is completed, again the next frame information comes here, and again inside that frame there are multiple samples and each samples will go through this algorithm. So it is a very low level algorithm, it's simple and powerful algorithm, a simple process we followed. So finally once all the samples are written, mixed samples are written into the file, we will just save that file here, write to file. Okay, this is a PCM file. Okay. Okay, so these are the GitHub links. PCM data mixing is the repo. So we will go through that, go through the code once, I mean the demo part once now. So this is the project I am discussing now. See, I will just quickly go through the flow once. So as we mentioned here, I take one complete frame, mixer frame, where all the data is computed. I mean all the data will be, so this is the buffer, output buffer. In this buffer, we should send the mixed frame. Okay. So first we'll read the data. We store this is the memory allocated, and then we read all the data, file 1 bytes, and then f read, yeah, and then this is the for the file 2. So finally we read all the data and then we get the information from PCM1 and PCM2. So now we will determine the number of frames. So now we will, for each frame we will call this mixer. So what this mixer iterates, it takes one frame and it iterates how many for each sample that frame. We'll go here and we'll pass frame 1, sample 1 and sample 2 value, and we will finally go through this algorithm, and then we return, and then we finally write it to the file. After each frame value, this buffer will be populated, and this buffer info is written into this output file. So like that we keep iterating for each frame, and this is the main application where you will be calling the above functions. Okay, so now let's quickly run it. So before running, I want to play what are the two different streams here. Since this is a PCM data, we need Audacity tool. So you need to install this Audacity tool, and you need to import the raw data. And this is my raw data, which is the first PCM file. So let's, this is, as I mentioned, this is 16-bit PCM, 2 channel, and this frequency is 44. So this data is correct, and then we can import with this data. Okay, so now if I play, you will be listening one audio. So it is a 10 seconds audio where there is no, only a background music is coming. Okay, so now let's put one more PCM, which is PCM2 file. Now let's import this. So this is also, this pics are correct, so I'm just importing it straight away. So now I am playing it. Now this is a different PCM data. Here a particular audio is coming. A singer voice is coming. A little bit of background music. Okay, so this is a singer voice is coming. A little bit of information is also there. So now let's close this also. So now let's so these are the two PCM files I have taken. So now let's mix these two PCM files. Okay, so I have already passed all the information here. So now I am just simply running this application. It's already built. Okay, so the application launched. About to launch. Okay, it got launched. It is running. Okay, it says this is the argument, and this is the Bluetooth PCM files, and mixing is done, and it is exited. So now let's close this, and then open our Audacity tool. Okay, this is my Audacity tool. So let's import the raw data. Okay, so this is the mixed version. So this is the correct timestamp now. So let's see now. So this mixed data also follows the same specification. Okay, because we did it from the number of frames, number of samples. So same spec, we have imported the data, we have written the data into the buffer, from there to the file. That's why you need to import with the same specifications. Okay, so now let's play. So the background noise, the background music plus the foreground voice, both should come here. Yeah. So as you can see here, the the foreground voice plus the background music, both together we mixed it, and this is how the mixing happens. Also the algorithm is very efficient, very simple. Will preserve the data representation, will not do not lose any data. Few little in the peaks data is lost. Apart from that, most of the data is preserved. That's how you do the mixing here. So yeah, I think it's, as I mentioned, it's a very bit simple and bit straightforward project, and a little bit of a common algorithm we are using, simple algorithm. This is about the PCM data mixing. So in the next project, we'll be discussing about a very interesting application called audio file streaming service application, where this particular project is kind of a background for Spotify, for YouTube Music, for all these streaming applications, audio streaming applications. They will be using this kind of architecture or this kind of application similar. So we'll be focusing on that project in the next video. So until then, keep watching our videos. Thanks a lot for your encouragement. Have a good day. Bye bye. Take care.